Mandelbaum, and in this video I'm going to introduce improved generalized automorphism belief propagation decoding. This is a talk I presented at this year's ISWCS. I will start with a short introduction in which I will motivate this work. Then I'm going to discuss generalized automorphism ensemble decoding and then show how we can improve it if we consider belief propagation decoding. Then I will finalize with some results and give a short conclusion. Let me start with a short motivation. For future communication applications, where short block codes are going to become more and more relevant. For example, if we consider low latency applications in 6G, or the communication of control commands, or an IoT scenario. However, for short block codes, there still exists a considerable gap between the performance of practical belief propagation decoding and optimal maximum likelihood decoding, as depicted also here for an exemplary code on the right-hand side. Here we depict the frame error rate on the y-axis over the dB over n0 on the x-axis. And in orange, we see the performance of belief propagation decoding compared to the performance of maximum likelihood decoding in black. And as you can see, we have still a considerable gap. However, we know that maximum likelihood decoding, even though it is optimal, is infeasible. On the other side, belief propagation decoding is a decoding algorithm which we can practically employ in hardware. Now, it is known that ensemble decoding schemes are a potential candidate to improve the performance of belief propagation decoding, in particular in the short block code regime. At this, they can improve the decoding performance and in the same time often reduce the decoding latency, which matches well the use cases that we are considering. Often, to improve the decoding performance or to be used in the ensemble decoding schemes, we exploit knowledge that we possess about our code structure, namely automorphism. Now I want to show how different decoding schemes use automorphisms at the receiver side to generate diversity, which we then can use to improve decoding. First, I will start by introducing the concept of multiple basis belief propagation decoding, which was first introduced in 2007 by Hehn et al. The idea of Hehn et al. Was that the decoding success of belief propagation decoding depends on the parity check matrix that is used for decoding. Therefore, they set up an ensemble decoding scheme, as can be seen on the left-hand side. We have p parallel paths, each trying to decode our received word y. And the idea is now that we employ a different parity check matrix to initialize our BMBF decoding in each path. Therefore, because of the different representation of the algorithm, one path might succeed when another one fails. Therefore, we can have p potentially different estimates after decoding, and then we choose the best candidate using an ML in the list. Recently, Jäkel et al. Introduced automorphism ensemble decoding, which generalizes MBBP. Again, we have p parallel paths. However, the decoding block is now arbitrary. So we could use different parity check matrices like in BBP, but we could also use the same decoding algorithm. The diversity is now mostly generated by using the automorphisms directly in the decoding path. So we have p different automorphisms pi of our code, and each automorphism is used to commute our received word y, which is then used for decoding. Because the decoding success depends on the noise representation at the input of the decoding, a shuffled received word might yield a noise representation where our decoding algorithm might succeed. After decoding, we have to undo our permutation, and then among those estimates, we choose the best one using an ML in the list rule. In a previous work, we introduced generalized automorphism ensemble decoding, which not only uses permutation automorphism, but a broader definition, which I will introduce later. However, in contrast to just permuting our received word y, we have to introduce a pre-processing and a post-processing that replaces the simple permutations we know from AE. In this work, our contribution is to improve generalized automorphism ensemble decoding if we employ BP decoding in each pass by merging the pre-processing of GID with the BP decoding. Therefore, and later see that we can improve the decoding performance. Now, I want to introduce the concept of the automorphism. The automorphism group of a code is defined as the set of mappings pi A, where pi is an element of the symmetric group and A is a non-zero element of our finite field, and pi A is defined as follows. So we permute our coordinates according to pi, and then we scale everything with our non-zero element. Therefore, I name this mappings pi A as scaled permutations. And now, in classical coding theory, for example, in the book of Max Williams and Sloan, the automorphism group of a code is defined as the set of all scaled permutations that map the code space again onto the code. This makes sense from structural properties such as the Hamming weight, because code words of same Hamming weights are mapped onto each other. However, in a recent work, we introduced the concept of generalized automorphism, Hereby, the generalized automorphism group of a code consists of all linear bijective self-mappings. Therefore, we drop the necessity that we have to use scaled permutation, but we can use arbitrary linear bijective self-mappings. It is known that a linear mapping can be represented by multiplication with a transformation matrix T as depicted. This brings me now to generalized automorphism ensemble decoding. As highlighted before, GID introduces a preprocessing to allow for generalized automorphism. Now that we have seen the definition of the generalized automorphism group, namely they are linear bijective self-mappings, we can find an inverse transformation matrix that maps the output of the decoding again onto an estimate of the original code word, and then we choose the best estimate using the ML and the list operator. In this talk, we're going to consider only the case where we have BP decoding in each pass. Now, on the next slides, I want to discuss some influences of the preprocessing. To this end, and for simplicity, we confine ourselves to binary codes, because the preprocessing is not simply performed over our original field, but we have to use the output of our channel. For example, if we have an AWGN channel, we can either use the received word y or the corresponding LLR values. And therefore, now we have to discuss the preprocessing. It is known that in the binary domain, the automorphisms are represented by a multiplication with T. So we obtain the code word x tilde after applying our automorphism T to our code word x as follows. So each entry of x tilde is a binary summation of the code bits of x according to a row of our transformation matrix T. Therefore, we can now see that the preprocessing can be performed using the box plus operation we know from the check node update in the belief propagation decoding, because in such a check node we also have a binary summation, and therefore to mimic the effect of the automorphism at the T at the receiver side, we pre-process the bitwise log likelihood ratios using the following equation, where we here also use the known symbol that is used for the box plus of. However, it is known that the pre-processing in GID yields an information loss, which I want to illustrate with the following setup. Here we have a box plus summation with an arbitrary number k of inputs, which are all fixed to 3. Therefore, the outgoing LLR is now a function of k, which we plot here. On the x-axis, we have the number k of inputs, and on the y-axis, we have the magnitude or the outgoing LLR message. As we can see, the higher the number of inputs, the lower the LLR, the outgoing LLR message is. And because it is known that the amplitude of the LLR indicates reliability, a row or a dense automorphism transformation matrix of an automorphism will yield a reduction of the amplitude and therefore an information loss in the preprocessing. Therefore, we introduce the term weight over permutation, which describes the number of non-zero entries of our automorphism minus n, and it's a good indicator if this automorphism can be used in GID or not. Now we come to improve generalized automorphism, belief propagation decoding. Our contribution in this work is to perform the pre-processing and the decoding jointly, and by this we can reduce the effect of the information loss and therefore improve GID. To this end, we consider the parity check matrix H, which is used for BP decoding, and as highlighted before, the pre-processing can be similar to a check node update, and therefore we can depict a full tenor graph used for pre-processing and BP decoding as depicted here on the left-hand side. Now, one path of GID looks as follows. We have our channel LLR, our bitwise LLR. Then, according to our transformation matrix T, we have some check node updates, which then yield the preprocessed LLRs, which then are used in the green part of the picture for iterative decoding. Therefore, the variable nodes for BP decoding here only use the preprocessed LLR values, which might or typically possess a reduced reliability. However, as we can see, this is a kind, not yet a full tenor graph, but we can rearrange the variable nodes and the check nodes as follows. And now we obtain an extended or a merged tenor graph, where the blue part still mimics the preprocessing and the green part mimics the BP decoding. However, now we can perform both jointly by iterating over this full graph. Hereby, we assume that we initialize the LLRs of the green variable nodes by 0. We could also use the preprocessed values. However, our simulation showed that initializing with 0 yields no degradation performance. However, this merged graph often possesses some structures that we can still prune. For example, if we have a check node of degree 2, as we can see here in the upper right corner of the picture, we can merge the connected variable nodes to a single variable node and therefore reduce the complexity of decoding because we have a lower number of nodes that we have to update. This then yields the pruned tenor graph, which is then used for decoding. So we do this for all parts, and then we obtain improved generalized automorphism ensemble decoding. This can also be represented using matrices. The merging of the preprocessing and the tenor graph of BP decoding can be expressed by just using the following merged parity check matrix, where we possess the transformation matrix in the upper left corner, the connection matrix which corresponds to the identity matrix in the upper right corner, and the parity check matrix in the lower right corner. And the pruning can be done as follows. We identify the rows of T with a single non-zero entry because they will result in check nodes of degree 2. For example, here we have the transformation matrix T, our arbitrary parity check matrix H for illustration. And as we can see, the first row of T has a single non-zero entry and therefore will yield the following row, which is a check node of degree 2. Now we identify in the identity part of our matrix where we have an overlapping 1 with another row in our parity check matrix. Then we sum those rows, which correspond to merging the corresponding nodes. And then we rule out the first row and the column corresponding to this row, yielding the parity check matrix of the parity check matrix corresponding to the graph after pruning. And now, due to the pruning, we are able to reduce the complexity of improved generalized automorphism ensemble decoding. Still, the complexity is slightly increased compared to GID because we have some more nodes on which the iterative decoding is performed, but typically the increase of complexity is very small. Now I come to some results and then to a conclusion. We considered some codes C2 and C3, which we designed in our previous work to possess certain generalized automorphisms. So here we have C2, it possesses a generalized automorphism T1 with weight over permutation 10 and second generalized automorphism with weight 13 over permutation. C3 is defined to possess a generalized automorphism with weight 5 over permutation and the second one with weight 6 over permutation. Also, we include some reference codes, namely a CCSDS code of comparable with same block length and dimension as C2, and a BCOH code with same block length and dimension as C2. In this talk, I will only consider a constant latency scenario in which all BP decodings perform 30 iterations of normalized mid-sum decoding. And all ensemble decoders use 3 paths with automorphisms, which is the identity matrix, the T1, which we have from the previous work, and the second generalized automorphism T2 is simply the inverse of T1. And then we perform Monte Carlo simulation using an AWGen with BPSK model. There's also a constant complexity scenario where we have a fixed number of total iteration. So if we have 30 iterations to spend, we give each path 10 iterations, yielding a total number of 30 iterations in our paper and also in our previous work. However, here we will only consider the constant latency scenario now. Here we depict the frame error rate over p over 0 and compare the code C2, which we constructed in the previous work, with its reference code. We can see that both in terms of NL performance and BP performance, the constructed code outperforms the reference CCSDS. Now we depict the performance of generalized automorphisms for ensemble decoding from our previous work. To this end, we consider the standalone performance of pass 2, which employs a transformation matrix T1 with weight over permutation of 10. As we illustrated before, the weight over permutation yields an information loss, which we can also see in the gap between GID pass 2 and BP decoding. Due to the information loss, the standalone performance of pass 2 is degraded. However, those paths can still be used to improve the overall performance as depicted in the curve of generalized automorphism ensemble decoding. However, if we now use improved generalized ensemble decoding, therefore the improved path structure, we can significantly improve the performance of the standalone paths. As depicted here, we observe a gain of about 0.6 dB at a frame error rate of 10 to the power minus 3, comparing both standalone paths. And this improvement in the performance of the paths also results in an improved performance of the whole ensemble. And therefore, we can here see that starting at the frame error rate, or so starting at the EB of 0.05, we observe an improved performance, and the gap to ML performance can be reduced to about 0.1 dB in the high SNR region. Now we come to the second code, C3. Again, we have here the performance of the code with its reference code. In this case, the PP performance is comparable. However, the ML performance of the BCH code is a bit better. Yet it's important to highlight that the ML performance is only relevant if we are able to approach it. And as we can see, we are still away from the ML performance. Therefore, let's consider here now the performance of generalized automorphism ensemble decoding. We can observe that path 2 in this case doesn't yield such a doesn't possess such a gap to BP decoding as in the previous case. This can be attributed to the fact that the mapping in path 2 now possesses a smaller weight over permutation and therefore a less severe information loss. Still, using the improved path structure, we are now even almost able to close the gap of the standalone performance of path 2 to BP decoding. Therefore, the improved path structure is again able to reduce the effect of the preprocessing. However, because in this case, generalized automorphism ensemble decoding is already quite good because of the small weight over permutation, we only observe a very small gain in the SNR regime. This brings me now to my conclusion. We introduced improved generalized automorphism ensemble decoding by merging the preprocessing of the generalized automorphism ensemble decoding with the tenor graph of BP decoding. Then we performed an additional pruning step on the graph, on the matrices, to reduce the complexity while decoding. This enables us to reduce the information loss in each paths. Therefore, the path performance can be improved significantly, but also typically we are able to reduce the gap between BP-based ensemble decoding and MLD. Thank you for your attention, and if you have any questions, feel free to contact me by email or here in the commentary section. Thanks.